Hello, and welcome to this training session on the Thermal Network Model, or TNM, developed for the Refile Aluminium pilot within the TRINEFLEX project. In this lesson, I will briefly explain the purpose of the model, how it works, and how it integrates into the overall TRINEFLEX framework. The TNM has been designed to accurately simulate the thermal behavior of the Refile rotary kiln with low computational cost to be operated in real time. It replaces a traditional finite element model, which is slow for real-time decision support. With this model, we can run fast simulations, generate recommendations, and synchronize with real data from Karen. Ultimately, it supports energy optimization and better process control. The motivation behind this model is straightforward. The rotary kiln requires rapid thermal predictions to support operational decisions, such as adjusting burner power or estimating internal temperatures. Finite element models are accurate but far too slow for this purpose. The TNM uses well-established heat transfer correlations, combined with modern optimization techniques, to achieve both speed and reliability. A thermal network model represents the system as a set of interconnected thermal nodes. Each node exchanges heat with others through conduction, convection, and radiation. Because the equations are simple and efficient, the model runs extremely quickly while still providing real scenario simulations, making it ideal for real-time applications. The TNM includes 7 temperature nodes: the flame, the exhaust, the combustion chamber, the aluminium, and both the internal and external kiln surfaces, as well as the surroundings. Together, these nodes capture the essential thermal behavior of the kiln. Here you can see a schematic representation of how they are connected. The nodes are linked through thermal resistances. Most of these combine convection and radiation, while the resistance between the internal and external kiln surfaces is purely conductive. Heat can flow in both directions depending on the temperature gradient, which allows the model to capture shutdown, startup, and transient behavior. The model can operate in 3 different modes. Mode 1 performs a full simulation and returns the evolution of all temperatures over time. Mode 2 provides an instant time result, giving current temperatures and heat flows based on sensor inputs and memorized stage. Mode 3 also synchronizes the model with real sensor data and returns traffic light indicators showing whether the system is within expected limits. The inputs depend on the selected mode, but generally include the operating mode, burner power, initial temperatures, scrap characteristics, and whether preheating or operation should be simulated. In Mode 2 and 3, the model also receives real sensor values to assess the current state. The outputs follow the same structure. Mode 1 returns full temperature curves, Mode 2 returns final temperatures and heat flows, and Mode 3 provides simple status indicators, green, yellow, or red, depending on how the real system compares to the model. The model is fully integrated into the TRINEFLEX ecosystem. It feeds into the decision support system and supports the Refile pilot by providing fast, reliable thermal predictions. This contributes directly to energy flexibility and improved process efficiency. And that's it for today's lesson. Thank you for watching. If you have any questions or would like further details, please feel free to contact the IDNA team.